Hello friends, welcome to EC Academy.
In this lecture, let us understand the concept of frequency in a discrete time signal. First, let us define the discrete time sinusoidal signal. A discrete time sinusoidal signal can be expressed as x of n is equal to a cos omega n plus phi. So here n should vary from minus infinity to infinity. So this is the representation of a discrete time signal, and this is the waveform that shows the representation of the signal x of n is equal to a cos omega n plus phi. Here a represents the amplitude, omega represents the frequency in radians, and phi represents the phase in radians. Here we can take omega is equal to 2 pi f. So if we replace omega is equal to 2 pi f in this equation, we will get x of n is equal to a cos 2 pi fn plus phi. So this is alternative way of representing a discrete time sinusoidal signal, and this 2 pi fn represents the number of cycles per samples. Now let us understand the characteristics of discrete time sinusoidal signal. The first property is periodicity of discrete time sinusoids. A discrete time signal is periodic only if its frequency is rational number. So this you need to remember. A discrete time signal is periodic only when the frequency f is a rational number. For a signal x of n is equal to a cos 2 pi fn plus phi to be periodic, there must exist a positive integer n such that we can have x of n plus n should be equal to x of n. So this you need to remember. For a discrete time signal to be periodic, the condition is x of n plus n should be equal to x of n, which means the signal is repeating itself after n number of samples, and the smallest value of this capital N that satisfies this condition is known as fundamental frequency. So the fundamental frequency of a discrete time signal is the smallest value of capital N that satisfies this condition. For a sinusoidal signal to repeat itself after n samples, the frequency must be such that 2 pi fn is an integer multiple of 2 pi. So in the standard equation of a sinusoidal signal, we are having the term 2 pi fn. So this 2 pi fn should be integer multiple of 2 pi. Only then the signal will repeat itself after n sample. So this is representing the property of periodicity of discrete time signal. Mathematically, we can write f is equal to k by n. So from this we can understand that frequency is inversely proportional to capital letter N, so number of samples, which means if we are having f is equal to 1 by 2, so this signal will be having 2 samples. So after every 2 samples, this waveform will repeat itself. So after every 2 samples, the signal will repeat itself. Here k and n are the integers in this above formula with no common factors. That is, these values should be relatively prime number. So this means the frequency f must be rational number, that is a fraction. If f is irrational, the sinusoidal signal will not be periodic. So f must be a rational number for a signal to be periodic. If f is irrational, then the sinusoidal signal will be non-periodic. Here let us understand by taking an example. If f is equal to 1 by 4, the sinusoidal signal x of n can be represented as a cos 2 pi into 1 by 4 n plus phi. So in place of f we have replaced 1 by 4. So since f is equal to 1 by 4, this signal is having fundamental period n is equal to 4, which means this waveform will repeat itself after 4 samples. Hence we can say x of n plus 4 will be equal to x of n. This represents the periodicity of the discrete time signal. Now let us understand the frequency aliasing in discrete time sinusoids. A discrete time sinusoidal signal with frequencies separated by integer multiple 2 pi are indistinguishable from each other. If we say indistinguishable, this means they are identical. Mathematically, if two sinusoids are having the equation x1 of n, which will be equal to a cos omega n plus phi, and x2 of n is equal to a cos omega plus 2k pi into n plus phi. So which means if you compare these two equations, these two sinusoidal signal are separated by the integer 2 pi. As you can see, you are having omega n plus phi here. Here we are having omega plus 2k pi into n. So which means these two sinusoidal signal are separated by the multiple integer 2 pi. That's why we can say these two signals are indistinguishable, or these two signals are identical. So this property focuses more on identity of two signals. So we understood that if the signals are separated by the integer value 2 pi, both the signals will be identical. So here k is an integer. So we will get the identity property due to periodicity of cosine signal. For example, if we add 2 pi to a cosine function, the value does not change, which means if we are having cos theta plus 2k pi, so this value will be equal to cos theta itself. So in this cos function we are adding 2 pi along with an integer k. This value will be same as theta. So in cosine function, here we are adding 2 pi along with k. So this cosine function will be equal to cos theta. So which means the frequency which differ by integer 2 pi will produce the same discrete time signal. This concept is also known as aliasing, which means that the higher frequencies fold back into the range omega between minus pi to pi. Thus only frequencies within this range are unique and meaningful in the discrete time signals. For example, a discrete time sinusoidal signal with frequency omega is equal to pi by 2 and another sinusoidal signal with frequency omega is equal to pi by 2 plus 2 pi will produce the same sequence or same signal. So as you can see, cos pi by 2n plus phi will be equal to cos pi by 2 plus 2 pi n plus phi. So what we are doing for this function, we are adding 2 pi. So these two sequences will be same. So these two signals will produce the same discrete time signal. Next property is maximum oscillation rate. The higher rate of oscillation of discrete time sinusoidal signal will occur when omega is equal to pi, which means at f is equal to 1 by 2. Here we know that omega is equal to 2 pi f. So if we take omega is equal to pi, so we can write above equation as pi is equal to 2 pi f. So we can cancel out these 2 pi and f will be equal to 1 by 2. So for this condition we will get maximum oscillations. So we can say the highest rate of oscillation for discrete time signal will occur when omega is equal to pi or when f is equal to 1 by 2. So for a signal x of n is equal to a cos pi n plus phi will produce the alternative signals which will be having positive cycle as well as negative cycle for each sample, that will result in fast possible oscillations. When omega is equal to pi, the signal has period of 2 samples. So this we understood. So if f is equal to 1 by 2, then capital N will be equal to 2. So that represents the number of samples. So when omega is equal to pi, f will be equal to 1 by 2, which means the number of samples will be equal to 2, which means it will be having one positive value and another negative value. So for every 2 sample, the signal will be repeating itself. This signal can be represented as x of n is equal to a cos pi n. Since cos pi is equal to -1, we can write a cos pi n as a into -1 to the power of n. If frequency is greater than pi, it will be mapped back into the range omega between -pi to pi due to aliasing. So this will effectively reduce the rate of oscillation. So when omega is greater than pi, so this will reduce the rate of oscillations. So in this property, you need to remember when omega is equal to pi, we will get the highest rate of oscillations, which means this signal will be having frequency as 1 by 2 and the number of samples in the signal will be equal to 2. If omega is greater than pi, it will reduce its rate of oscillations. Next is periodicity of discrete time sinusoidal signal. A sinusoidal signal to be periodic, we should have the condition x of n plus n should be equal to x of n. So this we have already understood in our previous property. So here capital N represents the fundamental period, which is the smallest positive integer that will satisfy this condition. For example, if we are having f is equal to 1 by 2, the number of samples in this signal will be equal to n is equal to 2, which means this signal will be repeating after every 2 samples. If f is equal to 1 by 60, which means the number of period will be equal to 60. So the signal will be repeating itself after every 60 samples. Aliasing in discrete time sinusoids. This property already we understood. The frequency outside the range omega between -pi to pi or frequency between -1 by 2 to 1 by 2, the signal will be having aliasing. The aliasing will occur because the sinusoidal signal with frequencies beyond this range produce same sequence as those within the range. For example, cos omega n plus phi will be equal to cos omega plus 2 pi k into n plus phi. So these two signals will produce the same sequence. The frequency range and oscillation. The maximum rate of frequency is achieved when omega is equal to pi. When omega is greater than pi, the oscillation rate decreases. So for maximum frequency, omega should be equal to pi. When omega is greater than pi, the oscillation rate decreases. The sinusoidal signal with omega is equal to 0 or 2 pi will result in constant signal. For example, you can observe here, this is the representation for omega is equal to 0. So we are getting a constant signal. We'll understand the application and we'll observe some of the waveforms. A discrete time sinusoidal signal are used in signal processing, digital communication and data analysis. So the discrete time sinusoidal signals have different applications like signal processing, digital communication and data analysis. So here, as you can observe, the different sinusoidal signal are represented here with different frequencies. These waveforms shows the periodic nature of the signal as well as the different rate of oscillations. As you can observe here, we are having omega is equal to pi by 8. So we can write omega is equal to 2 pi f. Since omega is pi by 8, so we can write this as 2 pi f. So we can cancel out these 2 pi and we can say f is equal to 1 by 16. So as you can observe from this waveform, so this sinusoidal waveform will be having 16 samples. After every 16 samples, this waveform is repeating. So this is for omega is equal to pi by 4, which means the fundamental frequency will be equal to 1 by 8. So after every 8 samples, the signal is repeating itself. And here f will be equal to 1 by 4 since omega is equal to pi by 2. So after every 4 samples, the signal will be repeating. This waveform shows the highest rate of oscillation where omega is equal to pi. So if omega is equal to pi, f will be equal to 1 by 2. Then for every 2 samples, the waveform is repeating. This is about the concept of frequency in a discrete time signal. Hope you have understood the topic. Thank you.